So I've had a lot of interest in my rocket-powered thermal mass. Behind me is my subterranean greenhouse, and I'm going to be trying to do a lot more videos on YouTube, more longer form YouTube videos to explain some of these things. I built this greenhouse almost 3 years ago now, and we started with a pit in the ground, a 4-foot deep pit, so that we could harness the power of geothermal from the earth, and we could also harness the power of the sun through passive solar. And it was not until a year later that I decided to build the rocket-powered thermal mass, which is essentially just a rocket stove inside of a giant thermal mass. So let's go inside the greenhouse. I'll save the greenhouse for another day, and we're going to talk about how I built the rocket stove. I'll go into more detail about the ins and outs. I did not really film a whole lot of the building, and I'll tell you why, because I honestly didn't know if it was going to work. So I didn't want to film a video and put out all this content about something that might not actually work. And now that I've tested it last winter, I had it operational, and this winter I just finished it. It is now about July 15th, or I'm sorry, January 15th, and it's cold. It's about 5 degrees today, high of 13. I'll put up the temperature readings for this week. It's going to be really cold, and then we're going to finally break that cold at the end of the week. But the next 3 days are going to be a good test. I've got citrus in there. I've got lemons and limes in the ground. I've also got olives and different things, and I'll be adding a whole lot of other house plants and different food-producing plants like coffee to the greenhouse this year. But yeah, let's go inside and check it out. All right, here's a good shot of the greenhouse. See, we're just starting to get some sun today, so let's go in. And so we built it right in front of our garage, so I get some of the benefits of that concrete wall. But this is my little anti-chamber. I need to do some work on it this summer, putting a real door on it. But you can see this is like the transition to down in the ground. I built this greenhouse out of recycled doors and windows for the most part, and tried to buy as little as possible. So this door is recycled. Okay, so now we're inside. So this is the lime, and the lemon. You can see I still have one Meyer lemon on. I'm waiting to harvest that guy. That's a good indicator of how cold it is outside versus it's actually warm enough in here to for these trees to produce fruit. So this has produced 3 lemons this year, and now that they're in the ground, I'm really hoping this coming year we're going to produce a lot more. You can see I also have my olive, got some rosemary, a rubber tree, aloe that flowered last year, and I got ginseng bonsai that I took from a cutting. There's some fig cuttings. There's some figs back in there as well. But yeah, I just added this. Let me zoom out here. So this is a seedling rack. I've got lights on it. So we're gonna start our seedlings in here in the springtime. Yeah, it just really helps because then we don't have to shuffle them in and out of the house, because seedlings really do best underneath natural sunlight. And even though I have lights here, they're mainly just for like germination and on days when it's cloudy. But other than that, they're going to be under the beautiful natural sun all spring long, which makes for stronger seedlings. So there I got my bay leaf. I got a begonia back there. And this is a calamandron. And you can see there's little fruits on there that are in active stages of growing. So calamandron is kind of like a lime. It's an orange lime. So, and now the reason that I'm making this video today is for this. This is the rocket-powered thermal mass. We'll zoom out so you can get a full picture. And as you can see, here's the burn chamber right here. So, this is the rocket-powered thermal mass. Why did I build this? Well, because the initial idea for building this greenhouse was to be able to keep my citrus and other plants out of our zone here in Ohio outside all winter long. You know, every year I'd take my Meyer lemon in, and it would barely survive the winter indoors, come back out, do pretty well, go to flower in like November, and then the process would start all over again. So I only got lemons like one time out of that. So anyway, when we got our property, I knew that I wanted to build something like this. And, you know, the most common complaint, I guess, or negative comment I get on my videos is that that's a lot of money for a $2 lemon. And, you know, it's not about the lemons at the end of the day. It's not about any of the plants. It's more about the experimentation along the way. I've learned a lot of good stuff and some incredible skills and knowledge about the Earth's functions through doing and through building. So this is the rocket-powered thermal mass. You know, I compiled a lot of different research to make this. The people that make this, my inspirations, like Paul Wheaton, guys like that. I think his name is Bill Faulkner, is another guy. But essentially what it is a rocket stove, which all a rocket stove is a Dakota fire hole, which is an ancient way to have a hot fire, especially in times when it's windy. So essentially what it would be a fire with a channel running underneath of it, and then basically an air hole underneath, and that would create a draft which would stoke the fire continuously. And so that's what this is. And throughout this video I'm going to show pictures and like just videos of what I was taking while I was making the rocket stove. Again, like I was doing this during the winter last year. I didn't know if it was going to work, so I didn't really do very well filming. I've also come a long way in my video making journey, so I didn't really have a lot of equipment at the time to be able to film properly, like a tripod, things like that. So anyway, this was all basically just the back wall of the greenhouse with all of the back walls exposed, and I started out by creating a base. And the base is essentially I poured a concrete foundation underneath directly onto the ground, and then I built this brick wall and used a bunch of just old bricks that we had actually dug out of this pit that used to be an old settling tank. And I also used a lot of old Hocking blocks, which are like road bricks, so they're pretty tough bricks. And so the thing with the rocket stove is that it's continuously stoking itself, which means that it burns incredibly hot. And that's awesome, because the point of this whole device here is not to just radiate heat. That's what typical wood burning stoves do. This is employing the thermodynamic forces of radiation, which is coming out of this barrel right here, and it's radiating the heat out from the top of the barrel and around, and this pipe is radiating the heat. The bench is also radiating heat, but really what we're trying to achieve here is the conduction, and the conduction from the bench. If I want to, I can sit plants on this bench, and they can directly contact and get the heat from that. And if there's nothing sitting on this bench, then I have a fan up here behind me that's currently off, and that will actually blow the hot air around the greenhouse. So right now it is about 5 degrees. This morning when I walked in this greenhouse, it was at freezing, which is a little bit lower than I'd like, but I didn't really burn the rocket stove that long. So the whole point of this rocket-powered thermal mass is insulation. We are trying to capture as much of the heat as possible from this fire that we are creating. So it's not about the immediate heat that I'm gathering, which is good though, because you know, it warms the greenhouse up, but we also have the light of the sun that's warming the greenhouse as well. So during the day. So when it's below freezing during the day and below freezing at night, and especially when it's close to zero like it is now, I'll burn the rocket stove. But if we are above freezing during the day, I do not need the rocket stove. So it doesn't get burned every day during the winter. It only gets burned in times of those deep winter days, you know, especially when we are below freezing and not getting any sunlight. So this is different than a traditional wood burning stove because it's constantly being stoked by the draft that's being created. You can see how actually raging the fire is in there, and it's only kindling that's in there. And you can also see that the fire is actually burning horizontally. The fire is getting sucked horizontally through the burn chamber and then back up through this heat riser, which is the barrel. But in that barrel is what's called a heat riser, which is essentially a masonry chimney that is made out of fire bricks. And then I've insulated that chimney with 2 inches of gravel and clay and concrete and whatever I could find, and caged it all up with chicken wire. And then I used a clay slip which is just clay and sand and water, to fire clay, which is extremely fire resistant. And I coated the entire chicken wire structure in the fire clay, so that way when I burnt the stove, it would essentially fire the clay and create a hard stoneware chimney that is in this barrel. And then all around the barrel there's a 2-inch gap. That is how the fire is getting sucked up through, and it swirls down in between that gap, and then it goes down to the piping. Now, believe me, I know that this is kind of a hard concept to understand, and so I'm going to cut back to when I was building the actual chimney and show you. I've been working diligently over the past week in order to fireproof this corner. This is the back corner of the greenhouse. Here are the fire bricks that are made to withstand temperatures of up to 2,000 degrees. Super important to dry fit everything as many times as you can before you build the final product. So here's my burn tunnel. I'm getting all my measurements. My stonework isn't that great, but I can fill all that in. I'm going to kind of explain the dimensions of this. So this is a 6-inch system, which means that I'm using a 6-inch flue up here, and that means that the stove itself is 6 inches by 6 inches square, and the dimensions are very important. The feed tube, which is the vertical tube right here, is let's say the 1, okay, and then the as terms of ratios, in this case it's 9 inches tall. And then the burn chamber, which is the horizontal chamber right here, that is actually going to be twice the length of the fuel chamber. So in this case 2, so it'll be 18 inches. So in the ratio 2 in inches, this one particularly is 18 inches. That means that the heat riser is going to be twice the height of the length of the burn chamber. Okay, so that's going to be a 4 in the ratio. So 1, 2, 4. Got it? And so in inches, that would be 36 inches. So 9, 18, 36 inches is the ratio. And what that ratio does is it creates the draft. It creates that depression that basically pulls the cold air in, because cold air wants to sink. So it pulls it in, sinks down, and then it gets drawn up through this flue. And this barrel is actually very important as well. So what the barrel is doing is the barrel is creating what's called a thermosiphon. And a thermosiphon is basically a difference in air temperature out here versus in there. And so the air is extremely hot in there. It's a lot cooler in comparison out here. And so that creates convection currents, which actually assist in drawing that air up through the flue, through that heat riser, and down through this barrel. Now, I told you there's a gap there. Now, the gap on top, you see I've put marbles up on top of here, but you could easily use this as a cook surface as well if you wanted. I don't need it as a cook surface, and the barrel I used has kind of a wavy top on it. So It's not necessarily for me, but if you can dial in the gap, the closer that you can make that gap at the top, between 1.5, 2 inches, the hotter that top will get. So also the bigger system you run, the hotter it'll get as well. So a typical system is actually 8 inches, but for this greenhouse, I thought that would be overkill. And also, you know, I do this on a budget. And so, you know, when you go up in size, everything gets more expensive. So this was an experiment, and a good one at that. And so I'm going to show you right now how I load it. So I've got this, this is just some sycamore that was kiln dried. It was all split up, so I couldn't really use it for woodworking, but it makes great fire material. I also burn firewood, but this could burn anything. So what I do to load it is I just have this little kindling pieces about 9 to 10 inches long, sometimes longer, but I try to do shorter pieces. And the key with this rocket stove is burning really dry, straight, small pieces of wood. This is a good example. Actually, that's not a great example, but let me show you a good example here. This is a great example of good fire material for the rocket-powered thermal mass. And the good thing about this is it allows me to use way less material when I burn. Because again, like I said, it's not about the immediate burn, it's about the energy that I'm capturing within this thermal mass that is actually going to be what helps me. Because I don't want to be up all night feeding this stove. I burn the stove until about 9 o'clock, and then I go to bed or go inside for the night, and I just coast off the heat the rest of the evening. So I burned it yesterday, and this morning I came in, and this bench was still warm. So I have some thermal imaging camera experiments, and I'll post a little snippet of that here. This right here is a thermal imaging camera, and it's going to give us a good visual representation of how the temperature is in this greenhouse right now. Now check out the bench. 90 degrees right in that spot right there. But the whole bench is around 60 to 70 degrees. And pan down to the floor here. We're more about 49, 50. 46, 47 up here. So this gives us a way better view of where the heat is in this greenhouse. Look at that. Even the stovepipe is 58 degrees just from the heat still radiating out of this bench. So here you can really see the design. The heat riser is twice the length of the combustion chamber. And the combustion chamber is twice the length of the fuel, which isn't really necessary. It's sucking just fine horizontally, but we're going to add that vertical J. So right now I'm just doing another dry fit of the stove before I mix together the clay slip, which is going to be clay and sifted sand and water, and that's going to be the glue that holds all these bricks together. I also put up a bunch of sheet metal and concrete board to kind of heat proof this area, as well as a big giant brick wall. After the stove is assembled, I'm going to assemble the 6-inch flue that's going to go all the way around this barrel and inside. You can see I cut a hole out with an angle grinder, and then that chimney is going to go up and out of the greenhouse, and this whole thing will be covered in cob, so that the cob is going to absorb all of that heat and then radiate it throughout this greenhouse, so that all of our plants, especially our lemons and limes, can benefit from that residual heat. I added equal parts fire clay to the sifted sand, and then I added enough water to make it very, very like a loose peanut butter. All right, got the second layer on. It's really hard to film because this clay is just so messy. But all right, guys, got the second layer on. It's looking good. It's starting to get a little bit easier now. Took a couple hours, but here we go. We got a 36-inch riser, 18-inch burn chamber, and then this will be a 9-inch feed tube. Let's see if it works. It works. The dragon lives. Here's a full picture of the rocket stove working. The air is getting forced back through and up, and so the fire is actually horizontal. And all this stuff that looks like smoke is actually steam, because all of this clay that I used to seal is still wet. So essentially I'm drying all of this very quickly. So I've kind of explained the mechanics of, this is the main portion of the stove right here. And you know, I know there's a lot that goes into that. Maybe I should make a video just on making the stove itself. After that, the hot air comes up and around this barrel and radiates that heat out. We lose probably about half of the temperature within this barrel system. Now I am the whole stove itself is insulated. This whole stove is insulated. There's a brick pad underneath, perlite, and a clay slip that is absorbing the heat under the stove. And then the entire stove is obviously surrounded by cob, concrete, and other masonry materials, bricks, whatever I could find really that holds heat. Because the denser the material, the more it holds heat. Water and stone are probably the best things that we can get as just regular people to hold heat. Because that's what it's all about. The bigger this bench is, the longer the flue is, the more heat you're going to hold. And if I had more space, I would have made this bench longer. Right now, this bench probably is only about 6 to 7 feet long. But once that hot air comes out and swirls around this barrel, it goes down. And it goes down in here. This is the first clean out of the flue. And so the air runs through the flue. It goes around. And you can kind of see that second clean out right there. It goes back. And then it goes back through. And there's a 55-gallon drum on its side in there that's full of rubble, concrete, all that stuff. The pipe's running through that. Goes up. And then out of the greenhouse. And so yeah, so as the hot air goes along this bench, the bench is absorbing the heat all along the way, and by the time it gets here, the air is much cooler than when it's here. So it was hard to get a high temp with the temperature meter because it only topped out at 350. But this is going to be the hottest part of the stove, and by the time it gets out here, we've lost about 3/4 of the heat that we were getting out of the stove. So the more heat that we can absorb in this bench, the longer that it will radiate out into the greenhouse. And so that means that I can burn the rocket stove during the day when I'm awake and out here, and then at night I can just use the extra heat that I've saved throughout the day, kind of like a bank account. So this is just like a bank account for heat essentially, and this is my savings account. Every day I deposit into my savings account, and then at night it gets slowly withdrawn. And so that way you know, I don't have to worry about these plants all night long, especially on a night like tonight when it's going to be 0 or below. And that's just a little bit too cold for the natural geothermal forces and things I have going on here. And at the end of the day, it's not just about these plants surviving, it's about them thriving. And I really want these plants to get to the point where these lemons and limes are growing up into the roof of the greenhouse and getting and becoming full mature trees. And I'll keep them pruned and all that kind of stuff. So that's a little bit about the rocket stove. And you know, if you guys have any questions, please put them in the comments. It's been a long journey with the stove, so sometimes it's hard to think about all the different you know, lessons I learned along the way. So any comments you guys give me help me a ton in thinking of what questions that you guys have that I can answer with this, because I want more people to do stuff like this. You know, this is a really cool way to add a unique and energy efficient thing to your home or garage or shop or anything like that, and you can really like customize it and make it your own. I chose to do a really unique finish on it using marbles, and I'll kind of go over that in another video. You know, I chose to make this an art piece, kind of. But, you know, you can go as ugly or as beautiful as you want. You can go as cheap or as expensive as you want. And really, the concepts are the same. The only difference is what the final result looks like. So, yeah, let me know what you guys think in the comments, and I'll make another video on the greenhouse, and I'll make more videos about this as well. So, thanks for watching.